In this video, we are going to present our project Chinese traffic sign recognition based on annotated street view images. Before self-driving vehicles can truly operate autonomously, they need to master Street Sign 101. Therefore, our project aims to train a CNN model that classifies traffic signs into 58 categories. In real life, traffic signs on the side of the street do not appear as clearly as the ones on the PowerPoint. Images might be taken under different weather conditions and from different angles from different distances. So self-driving cars will need to overcome all these issues. Now, let's take a look at our dataset. We have about 6,000 images divided into a training set of 4,000 and a test set of about 2,000. One major problem is that our data is highly imbalanced. As you can see from the bar chart, some categories have about 500 images, but some categories only have a few. Another problem is that the training set is quite small. Therefore, we use data augmentation to deal with both problems. We have learned several data augmentation techniques in class, but here, flipping the images is obviously not suitable. So we randomly augmented the data by using saturation, brightness adjustment, rotation, shifting, and central cropping. We divided the original test set into validation and test set, and only augmented the training set. Our first try was to expand the training set to about 12,000 images, and we made the data balanced at the same time. Our second try doubled the amount. Our baseline model naively categorizes all images as category 54 because it appears the most in the test set. Then we have our baseline accuracy of about 11.5%. Based on different degree of data augmentation, we tried many different models. My partner Ke will provide you more details.
The main methodology we use is TensorFlow and Keras. In addition, we use dropout regularization with a dropout rate 25% or 50%. We also use early stopping regularization, which gives out 25 to 30 epochs depending on which model we use. And we tried data augmentation. We tried original training set, the 12,000 training set, and 24,000 training set. We also use cross-entropy loss function, and in Keras it is categorical cross-entropy. We use mini-batch gradient descent with Adam optimization and ReLU activation function. We also try different network architecture and transfer learning. We include ResNet 50 and VGG16 in this presentation. First, we tried a self-designed CNN architecture. We self-designed many CNN architectures and we present the best two. And this is the one with 3 convolutional layers. And for the result, without data augmentation, after 30 epochs, the training accuracy is more than 98%, and the validation accuracy is more than 67%. But to our surprise, the one with data augmentation actually performs worse. To understand this, we went back to take a closer look at the validation sets. We found that the original validation set itself does not include any categories with low frequency in the original training set. In other words, we are only tested on what we learned extensively. So even the data without augmentation performs better than theory. And also with the data augmentation, we are only trained after 25 epochs, so it may also influence the result. Then we try another self-designed architecture with more layers to see if it will help. It includes 5 convolutional layers. And for the result, after 30 epochs, the training accuracy and validation accuracy are all lower than the first one with data augmentation. So we conclude that the network with few layers may work better because of the limitation of our training set size. Then we try transfer learning. All our transfer learning models are pre-trained on ImageNet, which is proved to be good at image classification task. First, we try ResNet 50 and unfreeze the last 2 layers of ResNet 50. For the results, for the 12,000 training set, the training accuracy is 97%, while the validation accuracy is still low. Then we try a much simpler VGG16 model, and we unfreeze the last 2 layers of VGG16. For the results, the 12,000 training set, the training accuracy is nearly 100%, and the validation accuracy is 40%. Then we try another data augmentation to see if more data helps.
We further augmented our training data into 24,000 images and tested the first self-designed model and the VGG16 model again. Both validation accuracies improved. To sum up, we tested multiple data augmentation degrees and multiple models. Generally, more data does contribute to a higher validation accuracy. Our best validation accuracy is with the first self-designed model. It's probably because our dataset is still medium-sized and fewer parameters is better for the model at this point. But we can also see that VGG16 has improved a lot after further data augmentation. Therefore, it is possible that if we continue to double the training set size, VGG16 is going to outperform our first self-designed model. Currently, we settled with the highest validation accuracy and went on to calculate the test accuracy. We yield a test accuracy of 82.3%, which is decent. Despite that, when we were testing real-life examples of traffic signs near NYU Shanghai, our model yields a surprisingly good result of being 100% accurate. Although we only tested with 6 new images, we are very happy with the result.
In this project, we learned to build CNN based on TensorFlow Keras. We also tried transfer learning based on Keras applications. We learned to choose a proper model with the help of data augmentation and some new regularization method. We think what can be improved in our project is that we want to try more variance and larger dataset to reduce variance, because in the VGG16 example, larger dataset does help. We want to combine object detection to do further application. In addition, we want to do AUC analysis because accuracy can be deceiving sometimes. So that's all of our project. Thank you.